Hi everyone, my name is Jimmy and I'll be starting off our presentation by introducing our group. We are group 11 and our group consists of Mark, Milena, and myself, and together we focused on how the color of a car's exterior might affect the interior temperature of the car. We chose this observation because we think it's something that many of us have experienced. On hotter days, it seems that lighter colored cars seem to stay cooler inside compared to a darker colored car. To explore this question, we looked at various sources that are peer reviewed. Our first source was by Pao, Goyo, and Sego, which was published in Materials Today proceedings. Their study showed that lighter colored exterior materials would typically absorb less heat because they reflect more sunlight. This supports the idea that a lighter colored car would stay cooler. Our second source was by Levinson and Akbari from the Lawrence Berkeley National Lab here at UC Berkeley. Their study focused on cool roofs or roofs in buildings. They found that lighter colored surfaces would significantly reduce heat absorption and lower energy needed for cooling. Even though the study looked at buildings and their roofs compared, which is different from cars and their exteriors, the same physics of light absorption applies directly to cars as well. Our third source was by Lahimir and colleagues. Their study specifically looked at cars and the types of materials and how it affects the interior temperature. They found that materials that are more solar reflective, like lighter colored covers, would reduce the interior temperature and also reduce the need for air conditioning. This closely relates to our topic and further supports our prediction that I will talk about in just a bit. Based on our background research, we formed the following hypothesis that the color of a car's exterior affects how hot the interior of a car can become. Darker colored exteriors will typically absorb more sunlight, thus leading to a quicker heating of the interior temperature and an overall hotter interior temperature when compared to lighter colored exteriors. In this experiment, the independent variable is the color of the car's exterior, while the dependent variable is the interior temperature of the car. Based off our hypothesis, we also made the following prediction that if two cars with different exterior colors are left outside under the same conditions at the same time, then the darker colored car will reach a higher interior temperature quickly and reach a higher overall interior temperature compared to a lighter colored car.
Thank you so much, Jimmy. The materials we use for our experiments were shoe boxes, uh, paint. In this case, we use white, red, and black. We use thermometers, plastic coverings, paintbrush, a timer, and a laptop to keep track of the results.
Procedure design. We will be examining if the color of a car's exterior affects the interior temperature of the car and its increasing rate of heat intensity. We will be using shoe boxes to represent the car and we'll be adding a plastic sheet to the shoe boxes to represent the car windshield. We will paint each of the boxes or cars to model. We will then place the boxes outside the sun, or we will be using a heat lamp to model the sun. Then we will measure the temperature inside each box for a set period of time using a thermometer. Procedure. Number 1, attach plastic coverings to the shoe boxes. Number 2, paint each shoe box a different color: red, blue, black, gray, and white. And then let the paint dry. Number 3, create a data table: lowercase t for temperature, uppercase T for time, and then use a laptop to record the times and temperature at each time. Uppercase T at 0, uppercase T at 10, uppercase T at 20, uppercase T at 30. Number 4, place thermometers inside each box and use identical positioning of thermometers for each box. And then lastly, place all the shoe boxes in a rooftop or outside area. But in this case, it'll be inside a controlled environment, indoors, and measure the starting temperature of the heat lamp when you start the timer. Record and measure the temperature of each car every 10 minutes for 30 to 60 minutes, but in this case, it'll just be a total of 30 minutes by lifting the lid of the box. Record the temperature of the inside the box in degrees Fahrenheit in the data table. Experimentation and data acquisition. Shoebox heat absorption experiment. Setup: 3 boxes, white, red, black interiors, placed 5 inches below a 150 watt bulb. They all started at 73 Fahrenheit interior temperature. A thermometer was placed inside each box only at each interval to record temperature, then removed after each reading for accuracy. Temperature recorded every 10 minutes for a whole 30 minutes. Results. Each box started at 73 degrees Fahrenheit, and then at 10 minutes, the white box became 79 degrees Fahrenheit, the red box 82 degrees Fahrenheit, the black box 84.7 degrees Fahrenheit. And then at 20 minutes, 81 degrees for the white box, the red box became 83 degrees Fahrenheit, and the black box was 84.9 degrees Fahrenheit. And then the final 10 minutes, which is at 30 minutes, white box became 82 degrees Fahrenheit, red box became 83.5 degrees Fahrenheit, and the black box became 85.5 degrees Fahrenheit. Data analysis and conclusion. Based on the experiment's results, the black box or car recorded the highest temperature compared to the red box and the white box. The red box recorded the second highest temperature, and the white box recorded the lowest temperature. At 30 minutes, the black box was 2.5 degrees Fahrenheit warmer than the red box, while the red box was 1.5 degrees Fahrenheit warmer than the white box. This demonstrates the conception of light absorption, where darker colors or surfaces absorbs more wavelengths of light, which is converted into heat, while lighter surfaces absorb less or reflect more wavelengths. The results support our hypotheses that darker colors absorb more heat than lighter colors. Possible sources of errors that could arise were condition of the boxes and heat loss. Some of the boxes were older than others, which could have affected the results, and there might have been potential heat loss when opening the box to read the thermometer. For future reference, the next experiment could include more different shades of colors or materials to possibly test out different wattages for heat lamps to simulate different temperatures. Our group research and experimentation have led us to conclude that the concept of light absorption, where darker colors or surfaces absorb more wavelengths of light, which is converted into heat, while lighter surfaces absorb less or reflect more wavelengths. That concludes Group 11's video presentation. Thank you so much.